This video is for the paper 1A questions on E3 radioactivity. And there are 22 questions, and I'm trying to keep these videos to about 15 minutes, so we may have to do this in 2 goes. All right, let's roll. So the first question deals with a nuclear fission reactor, which I think was part of HESSEL, but I'm not sure if terms like moderator and control rods are in there. But in a nuclear fission reactor, the radioactive material sends out neutrons and heat, but then if the neutrons are not absorbed, those neutrons go on to create even more nuclear reactions, and you get a chain reaction, which is what happens with a nuclear bomb, and the whole thing explodes. So the control rods absorb the extra neutrons, so the process can just kind of percolate along without chain reaction happening. And then in order for the neutrons to create the next reaction, they also need to be slowed down, and so the moderator is in there. But the heat exchanger does not transfer energy from fuel rods to the moderator. Rather, it transfers them from the fuel rods to the turbine unit that's going to turn into electricity. The moderator's job is to slow the neutron down. So we have 2 control rods are good absorbers of neutrons, and 3 moderator slows neutrons down. That is the correct statements, choice C. So in this reaction, we have beta plus decay. So beta plus is the antiparticle of a actual beta, which is an electron. And so beta plus has a nucleon count of 0, but a proton count of 1 because it's positive. And so it's not A because we have carbon 14 turning into nitrogen 14, but that's 6 going into 7, and so the electron would be -1, and so. But wait a second. No, that does work, actually. But the electron is normal matter, and so this neutrino here would actually need to be an antineutrino, because if normal matter is created, antimatter also needs to be created, and so that I put the bar on there. So that is a normal neutrino, and so it can't be A. Also, there's no beta plus particle there, and so we have beta plus particles in B, C, and D. And so if we look at B, we have the beta plus particle, but beta plus would be 1. And so 6 yields 7 plus 1, that's 8. That's not going to work. Also, we would not have an antineutrino here. We would have a regular neutrino because the beta plus particle is itself an antiparticle. Then we have magnesium becoming sodium, and while the number balance does in fact work out, and that looks good, the beta particle is itself an antiparticle, so we would not have an antineutrino here, so that's not good, and we're left with D. Magnesium 23 becoming sodium 23 plus a beta plus particle, so that works based on the numbers. 12 yields 11 plus 1, and a normal matter particle, a normal electron neutrino. Because we made an antiparticle, we would need to make a normal matter particle to go with it. And 2 is D. That does agree with the marks. Okie dokie, let's take a look at number 3. So binding energy, as the protons and neutrons combine to make an elemental product, their combined mass of just all of the protons and neutrons is greater than the mass of the elemental product. That missing mass, what they call the mass defect, becomes the binding energy to hold the atom together, that oxygen atom in this case together, by E equals mc squared. And so the binding energy of the nucleus, so the mass of the oxygen is going to be 8 times 8 proton masses plus 9 neutron masses, but, okay, number 3, it talks about rest mass, oxygen 17 nucleus is MO. This is what's the binding energy of the nucleus. Well, binding energy as the protons and neutrons combine, that combined mass is greater than the elemental product because that elemental product is missing that mass defect. That mass defect, which just means missing mass, becomes the binding energy to hold the oxygen nucleus together by E equals mc squared. And so the mass of the oxygen is 8 proton masses and 9 neutron masses minus the mass defect. So if we solve for the mass defect to get the binding energy, that's 8 proton masses plus 9 neutron masses minus the mass of the oxygen itself. And since E equals mc squared, we just multiply that mass defect times c squared, and we get choice A. I just realized I repeated myself a bunch of times. This is what happens when I start and stop when I'm making my recording. I tend to repeat myself, but I did explain the problem, so there you go. Sorry about that. Next question. So in number 4, we have a neutron bombards with uranium-235 to yield barium-141, krypton X, and 3 neutrons in the process. And if we let those neutrons rip, they'll create a chain reaction, go into a bunch of other uranium, and create, the nuclear bomb. If we can absorb 2 of those neutrons, and then let 1 neutron go on, it'll just continue the process without escalating. And that's a nuclear power plant. But anyway, so nucleons in the krypton nucleus. So we have 1 neutron and the uranium-235 giving us 236. And then on the product side, we have 141 plus X plus 3 neutrons. And so the nucleon count for the krypton is going to wind up being 92. And then it says the binding energy per nucleon of krypton over the binding energy per nucleon of barium. We know that the binding energy per nucleon of iron is the most. And so, iron has the highest binding energy per nucleon. So the closer you are to iron, the higher your binding energy per nucleon. And so krypton is 36 and barium is 56. So if we're doing binding energy per nucleon of krypton over barium, krypton is bigger than barium for binding energy per nucleon, because krypton is closer to iron than barium is. And so that ratio is going to be greater than 1. So the krypton nucleon count is going to be 92, so that gets rid of C and D, and the ratio is greater than 1 because krypton is closer to iron, which has the highest binding energy per nucleon, and so that is A, which checks with the mark scheme. All right, let's take a look at number 5. So with number 5, we have, says radioactive substance, half-life of 5 hours, decay constant lambda, at 20 hours there are N nuclei present. What's the activity at time 5 hours? And so 20 hours later, that is, it's 3 half-lives after the 5-hour half-life. And so I made a little chart based on the half-lives and if at time 0 we have N naught as the original count, after 5 hours each time, it's half of what it was. But we're comparing 5 hours and 20 hours, so 20 hours is 3 half-lives later, and so that's half and half and half again. So at 20 hours, it's 1/8 what it was at 5 hours, or it's asking about 5 hours, so 5 hours is 8 times what it is at 20. So at time 20, we have N nuclei, and so at time 5, we have 8 times that, which would be 8N. And so we know that, and that's about the activity. So the equation for activity is that A is lambda N, or it's lambda N naught e to the negative lambda T. Now, my first instinct was to go ahead and solve for lambda, which we can do since we know the half-life, but all of the answers are in terms of lambda, so we don't actually have to solve for lambda here. We just have to realize that at 5 hours, the count is 8 times what it is at 20 hours. So therefore the activity is lambda N, which N would be 8 times, so it's 8N lambda, which is B. Number 6. A sample of the artificial element seaborgium-265 is created with 4 times 10 to the 22 atoms. Seaborgium-265 has a half-life of 15 seconds. How many atoms of seaborgium-265 remain after a minute? So our starting count is 4 times 10 to the 22. Half-life is 15 seconds, so what's the count after a minute, which is 60 seconds, which is 4 half-lives. And you can maybe work this out using the equations, but you could also noodle it out, realizing that 60 seconds is 4 half-lives. And so if our start count at time 0 is 4 times 10 to the 22, 1 half later it's 2 times 10 to the 22, 2 half lives is 1, 3 half lives is a half times 10 to the 22, or 5 times 10 to the 21, and then 1 more half life is half of that, 2.5 times 10 to the 21, which is choice A. Number 7, beta decay. Energy of the emitted beta particles is continuous. This is explained by the what. So what do they even mean by the energy is continuous? All right, so emitted betas, they can have any energy from high to low. So the energy is continuous. They can have any energy they like, but the total energy has to be conserved. So if the beta particles can have any energy they like, there needs to be some way to account for high energy, low energy. The total energy is constant. So another particle is emitted with the beta particle, being the neutrino. The neutrino accounts for that extra energy. If I have a high energy beta, that would be a low energy neutrino. If I have a low energy beta, it would be a high energy neutrino. The neutrino is very small. It has no charge, so that the charge balance, the conservation of charge, is maintained. And then if a regular beta particle, like an electron, is emitted, then an antineutrino is emitted to counterbalance the matter-antimatter pair. But if a beta plus, if a positron is emitted, then that's an antiparticle, then a regular neutrino is emitted. But the existence of the neutrino takes care of the continuous nature of the energy of the emitted beta particle. So that's D. Number 8. 8 starts here and then apparently breaks over here. So this is number 8. All right. This is a repeat. Same as number 6. Let's move on. Number 9. Number 9, so 8 and 9 are repeats, but number 10 is not. Okay, so number 10. Which statement about atomic nuclei is correct? The density is what? And so number 10 is actually a topic E2 question. Sorry, that's topic E1 question, actually. So just to kind of go back over that quick, because it's worth a review, we know that density is mass over volume. The volume of a sphere for a spherical nuclei is 4/3 pi r cubed, and the radius of a nucleus is the Fermi radius times the atomic number to the 1/3. And so the mass of a nucleus is the mass of a nucleon times the atomic number, because that's the number of nucleons it has. So if we do rho is A times the mass of a nucleon divided by 4/3 pi r naught a to the 1/3 raised to the third, then we have A in both the numerator and the denominator. The atomic number cancels out, and so that density depends on, why did I write M2 here? The atomic number times the mass of a nucleon divided by the atomic number again times 4/3 pi Fermi radius to the third, and so all of those things are constant, and so the density of all atomic nuclei is constant for all nuclei. But that's not really an E3 question. Anyway, number 11. Eleven is an interesting way to represent half-life. So the graph shows two nuclides, X decaying into Y, and then S is the crossing point for the two curves. So since S is the crossing point, the amount of X equals the amount of Y, half of X is turned into Y. Half of X. So in other words, S is the half-life for X. We know that half-life is the natural log of 2 divided by the decay constant, so the expression for S would be the half-life, which is natural log of 2 over the decay constant, A. Next question. So for number 12, talking about the decay constant, we know that the answer is an A or C because a number or a probability has no units, and we know that if the time for the half-life, the time for half of the sample to disintegrate is natural log of 2 over the decay constant. The decay constant is natural log of 2 over the half-life. So the units would be 1 over seconds. So it's pretty much per unit time. So we have per unit time per unit time. So it's not A or C. So we're left with number of disintegrations per unit time, or probability that a nucleus decays per unit time in the radioactive sample. So it's going to be choice D, but let me show you why by talking about the activity. So we know that the activity, which is a rate, is lambda times n, and n is the count of the remaining nuclides. Now, what's the activity of radioactivity going to be? If we look at the decay constant, first of all, activity is a rate. So yeah, A is a rate and n is a count. So the lambda must be per unit time. But how much radioactivity you get in the rate of radioactivity, and so whether we actually have radioactivity off the base count, is whether or not a nucleus is going to decay. So that activity rate, how much radioactivity we get, is the probability per unit time that the actual count is going to be affected. Not necessarily the number of disintegrations per unit time, but whether or not you're actually going to get any radioactivity that'll affect the activity rate. So yeah, it's a probability of decay, probability the nucleus decays per unit time. So 2 of the problems were repeats. So we're about halfway. In about 15 minutes, I'm going to cut the video here and finish the rest in another video.